Now that we've established a mathematical relation between the harmonic oscillator problem we've already solved and the electromagnetic mode, we can start to think about the quantum mechanical states of that mode. Since the electromagnetic field will in general have many modes, the first thing we need to do is to set up some notation to let us work with them all. Basically, each different mode, such as different plane waves going in different directions, will be a different harmonic oscillator-like entity. So we need to distinguish between them in the states and the operators we construct. Otherwise, though, we're going to be able to use all of the notation and ideas we have from our earlier discussion of the harmonic oscillator. So, to show which mode the operators refer to, we commonly use the index lambda to index the different modes. Lambda here does not necessarily mean wavelength, it's just an integer index, and this is a common notation. With that new notation, we have for a given mode, for example, an angular frequency omega lambda instead of just writing omega, because we want to be specific about which mode it is that has this frequency. With that notation, for a given mode, we'll also have a Hamiltonian, which we index now with lambda, creation and annihilation operators, also indexed with lambda, and a number operator, indexed with lambda. We can also label the eigenstates similarly as psi lambda n, with this being the nth eigenstate associated with this particular mode, lambda. And we can also change here to using a coordinate xi sub lambda instead of just xi, since each different mode will have its own corresponding coordinate. With this notation, we use some harmonic oscillator results that we worked out before to give us the key relations for the electromagnetic mode lambda. So our Hamiltonian for this particular mode lambda becomes, obviously, h bar omega lambda times this parenthesis group here with the creation operator and the annihilation operator for the mode lambda and our half, of course. And the number operator similarly as before, but with the lambdas indicating the modes we're talking about. And hence we get our number operator relation in this new notation as before. And the corresponding eigenenergy as before, but now with the lambda in the subscript here to indicate we're talking about mode lambda. This is all very straightforward, but we have to remember to put in the lambdas now because we're talking about one specific mode here. And this energy, as we would expect, grows in proportion to n lambda. That is, the energy increases as n lambda times h bar omega.
Now, we should pause here to note something quite remarkable. Our model here has just given us photons. They have just appeared suddenly in front of us. The energy states of this mode, with their quantum number, n lambda, obviously are expressing the quantum mechanical state of excitation of the mode. A state excited to its nth level has an energy n times h bar omega more energy than it had in its lowest level. This is the same thing as saying that there are n photons in the mode. We will go on here to develop the mathematics of this some more. That mathematics will completely describe everything that can happen to the level of excitation of this mode, and indeed its full quantum mechanical states. That mathematics does not require that we introduce the word or the term photon. It does not require that we separately introduce the idea of a quantum mechanical particle that we could call a photon. Indeed, now that we've set up this mathematics, we actually never have to introduce the idea of a photon as a separate concept. But the behavior of the levels of excitation of this mode is exactly what we meant by the idea of photons in a mode. It's important to emphasize that everything we understand about what a photon is and does is something that emerges naturally from this process of quantizing an electromagnetic mode. We do not need any separate idea of photons as particles. Indeed, we could even argue that life might be simpler if we never introduced the idea of photons as particles. That is entirely a matter of taste, because we have all we need in this mathematical description to work with the physics here.
We also have, of course, the commutation relation, just like we had before, but with the lambdas everywhere in the relation. And we have our lowering relation, which takes the state with n lambda photons in a mode to the state with n lambda minus 1 photons in the mode. And so we now call this operator the annihilation operator for mode lambda because mathematically it annihilates a photon from the mode. And similarly, we have the raising relation here, which we now call the creation operator relation. This becomes the creation operator because it's creating a photon in the mode. We will also have that trying to take a photon out of an empty mode will lead to a zero result. This is exactly the same kind of relation we had before. And we will also be able to write, as before, that the state lambda n, or with n lambda photons in it, can be constructed by operating n lambda times on the empty state, this state with 0 photons in it, and of course we have to put in our 1 over root n lambda factorial to keep this normalized. Though now, of course, we think of this state as a state with n lambda photons in mode lambda, rather than as simply the nth state of a harmonic oscillator, although these are entirely equivalent ideas. Now, we've quantized the electromagnetic mode by analogy, leading to an abstract set of results. Do we have to be this abstract? Can't we use the wave function like we did before? That was something that seemed to have more meaning, perhaps. At least we could visualize it. Now, here, this idea of a wave function does have some meaning, though it is quite different, for example, from the wave function that we had before when we were thinking about an electron, where we visualized the wave function as a spatial function. Just as before, we have for the state with no photons in mode lambda, this expression here, which has a wave function-like form as a function of this coordinate xi lambda. But now if we work backwards to find the physical interpretation of this coordinate xi lambda, we find that it's really an amplitude of a magnetic field. Here's the xi lambda, there's some other stuff multiplying it, but it's really expressing an amplitude of a magnetic field component. In other words, as we've said, xi lambda is, in a dimensionless form, the amplitude of the mode of the magnetic field. It's not a spatial coordinate. For example, we can interpret this modulus squared here of psi lambda 0 of xi lambda as the probability that in this state of the electromagnetic field mode lambda, the mode has dimensionless amplitude xi lambda. The probability is therefore a Gaussian, 1 over root pi times the exponential of minus xi squared lambda. We would find related results for the states of the mode with more photons.
Note that this quantized version of the electromagnetic field is behaving very differently from what we might expect. There are at least two specific behaviors here that are very different from classical electromagnetic fields. First, in a state with a given number of photons, the magnetic field amplitude is not a fixed quantity, but is rather described by a distribution. Second, even with no photons in the mode, the magnetic field amplitude is not zero. Similar results can be stated for the electric field mode amplitude. The presence of such amplitudes of the electric and magnetic fields, even with no photons present, is called vacuum fluctuations. The states with specific numbers of photons correspond to the eigenstates of the Hamiltonian or the number operator. But, perhaps surprisingly, these states do not have precisely defined electric or magnetic field amplitudes. For states with definite numbers of photons per mode, we are not recovering anything like a simple oscillating electromagnetic field. We will come back later on to describe quantum mechanical states that do correspond fairly well to our simple classical notions of electromagnetic fields and waves. But these are not states with specific definite numbers of photons in a mode.
Now, though we may be sometimes interested in these distributions of magnetic or electric field amplitude, which we can deduce from this wave function-like object, we're generally much less interested in these than we were in the probabilities of finding particles at points in space. As a result, in the quantized electromagnetic field, we make relatively little use of these wave function objects, but they are there if we want to use them, and they do have a meaning, but it's not a spatial function. Most of the results we're interested in, such as processes adding or subtracting photons, can more conveniently be described through the use of operators and state vectors. Typically, the basis set we work with and the resulting state we will use will not be written as these functions, psi of xi lambda, of the amplitudes xi lambda of the fields in the modes. But we'll write them instead as basis vectors corresponding to specific numbers of photons in a mode. That is, we're much more likely to use these kinds of states and this kind of notation. Either one of these would do. Since we are not really thinking so much about wave functions anymore, we often abbreviate the notation just to saying the number of photons in that mode.